Hi, this is Aaron Jerome at Jerome Electronics, and I'm going to record another video for YouTube. This is going to be my students' introduction to an application called Multisim. You're listening to Mark Knopfler, one of the best guitar players on the planet. Great voice, crafty lyrics. He's really good at lyrics, and really enjoy his music, but that's not why we're here. But great music. Check it out. Dire Straits, Mark Knopfler. Okay, what you're seeing on the screen is actually from the National Instruments website, and they're talking about Multisim. Again, this is Multisim. This is the application that we use in our class for designing circuits. My students can actually download it for free at home, and how I do it may not be the same way that you can arrange for students to do it, but this web page here, all I did to find this was key in a search for Multisim for education, and got to this screen, so it shouldn't be hard for you to find, and then you can get it downloaded. And maybe you can get it for your students or as an educator. It's pretty expensive, but it's well worth it if you buy a copy of it. But I will be demonstrating this, and if you feel like you need it, you should investigate it more. If you're one of my students, talk to me, and I will tell you how to get this at home, and you'll be able to log into this to get your work done. Okay. So Multisim, the interface looks like this. This is just a random image from the internet. Looks like they're making an up and down counter, which we do get into a little bit later. But I thought it was kind of interesting to show the interface here. Now I'm going to go to the live interface. That's not it. I'll talk about that later. But this is the live interface. And when you open up Multisim, this is pretty much how it looks. And there are things that I need my students to do right away, a couple of changes to make, and so forth on their computer. They take notes on these things, and then if they need to remember this, they can just look in their notes. All right, so, pardon me. One thing I need to remind students, I remind them this during as I lecture, because I actually have them all do this together, and this is a fun toy, and if they play with it, they could get lost. But I guess that's not as important. If it's on YouTube, they can always pause, rewind, do whatever they need to. So I guess the real first thing that I like to tell my students how to do is run their scrolly wheel. If you run your scrolly wheel, it zooms in and out. And that's okay, except when they want me to come over and help them troubleshoot a circuit, I'd rather see the scrolly wheel scroll instead of zoom. Also, while we're at it, let's get a little more screen real estate. You can eliminate this design toolbox temporarily. You can always bring it back later. And they call this the spreadsheet view. And now I can scroll it in and out. I can press down on my scrolly and drag this around. I'm going to actually, you can zoom in. I'm going to actually zoom in. And the reason I'm doing that is so you can see it scroll. It doesn't scroll if it's smaller than the screen. To make it scroll, we're going to click on Options. Write this down in your notes. Global Options. And then we're going to click on the General tab, and then click on Scroll Workspace, Apply, OK, and now when you roll the scrolly wheel, it scrolls instead of zooms. What if you still want to zoom? Well, that's pretty easy, and most of my students know because this is a standardized control among many applications. You click on the control and scroll, and it still zooms, and so that's how that's done. The next thing is the size of this sheet. I like to change it so it's large, because otherwise when students build stuff, they tend to run out of space. They need to know how to make more space, but I like to start with a larger sheet as well. So we click on Options again. This time, we're going to click on Sheet Properties, and then we're going to go to the Workspace tab, and right now it's set up as a regular size piece of paper. It is a portrait that's 8.5 width by 11, which is standard size, in inches, and I like mine to be bigger. I like to make it size 11 width and 17 height. And then I click Apply. I like it to be portrait, but it could also be landscape. I like to apply and then click OK. And there it is. It's a larger screen. Well, this leads us to another problem, and that is if I were to design a circuit on here and then print it, it would shred a forest. It would crank out 4 pages trying to show the entire thing. So one more thing that I have my students write down, is to click on File, and then go to Print Options, and then go to Print Sheet Setup. Under Print Sheet Setup, look for the Zooms area, and then click on Fit to Page. So whenever this prints, it will print on a single page, not 4. Okay. With that done, what I also like to do right at the beginning is have students place some text right at the top. And so this is how you do that. You click on the Place menu item, and then click on the Text Tool option. Click somewhere on the screen, and then I like to have students always, on any documents they turn in, I prefer them to have what I call the DPSN brand. That stands, DPSN stands for date, period, seat number, and name. And so the date here, it is, I tell my students they can use any date format they want. This recording is on October 9th, 2023. So, but my favorite way to put a date in is to use 2 digits for the year, 2 digits for the month, and 2 digits for the day. So the year is 23, and the month is 10, and the day is 9. And then I have them use the space bar about 10 times, I suppose. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we put the period. You got the date, the period, the seat number, and the name. And so the period, I don't know what period this is. Class period, I don't know, 7. And then another 10 spaces. Seat number. I have in my classroom tables that have 2 students per table, and then computers around the perimeter of the room. And there are, 3 wide, 4 tables deep, 2 students per table. That's 24. So I actually name each table according to military designation: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, things like that. And so students know they're at table A, B, C, D, E, F, G, H, I, J, K, L is about as far as we go. And each table has 2 seat places. So let's just say this is going to be Kilo 1. Kilo 1. There's Kilo 1 and 2. There's 2 students per table, so every alphabetical designation, and then a 1 or a 2. 1s are on the left and 2s are on the right. Another 10 spaces, and their first and last name. Now, I tell students after this that what they should do, they can click into the white space. You can click twice into the white space, and there's your text. But if you want to edit it or move it, you can just click and drag. And I tell them to click and drag it as close as they can to the upper left-hand corner without crossing the lines. And there it is. It's there for when they want to turn something in. Okay, in a previous video, I just introduced students to all of the important gates, the important logic gates, and explained to them what they do. And if you haven't gone through that video, you probably won't understand this one unless you understand those gates. They are the 0, 0, the NAND gate, the 0, 2, 2, the NOR gate, the 04, the NOT gate or the inverter, the 08, the AND gate, the 32, the OR gate, the, the 86, the XOR gate, I call it the XOR gate, and then the 266, which is the XNOR gate. And I also told them about the buffer, but that wasn't actually listed in the group. I do talk about it, though. And so now what we're doing is we're designing simple circuits in Multisim so that students can actually see these gates in action. They also learn from this assignment how to find components, connect them, put them all together. And then we talk about elegance as well of circuits, and I will be talking about that here. So for the first circuit, I like to always start with the AND gate and then evolve to the other gates from there. So what we need to do is place some components on the screen. The normal way to get components for Multisim or in Multisim is to right-click in the white space on the screen and then click on Place Component. Then, of course, there are several ways to get several things, but what I suggest you do is make sure that group in the selected component window, make sure that the group says all groups and that all families is here at the top. Then come over to the component window, and we're going to get a source of power for the screen. And you should write this down in your logbook because it's not intuitive until you get used to it. And the way to find power, to search for the power component, is to type VCC into this window. Now, quite often, when we put a component into the window, you get lots of options to choose from, but it knows exactly what we're looking for. This is the power. It looks like the letter T. It's got a horizontal component. It's got a vertical component as its schematic symbol. And you can just double-click on the blue line if that's the one you want, or click OK. I'm going to double-click on the blue line. There is my source. I'm going to put it right about here. I tell students to place this at the location. You click on it to place it. And I don't want any more, so I'm just going to click on Close on the placing window. And now I've got this VCC. And what I try to do is have students become a little bit familiar with the coordinates. So the vertical piece on this VCC schematic symbol, I try to line that up as close to below the 0 above it as possible. You can click on it and use the arrow keys to move it, or you can click on it and drag it anywhere you want. But that's probably about as close as I'm going to get. Maybe right there is good. I also try to make the horizontal component of the schematic goes right across from the A. There are reasons for me being so specific about placing components for now, which won't matter later, but what I'm trying to do is give them coordinates and to make this as efficient as possible. Okay, VCC means power. We'll also need a ground. So I'm going to right-click click on Place Component, and then for power, might want to write this down, we're going to use what's called a digital ground. And to get a digital ground, we would put DGND in the search window. There's only one. It looks like this in the little window. I'm going to double-click on that, put my ground just down here somewhere. I'm going to move it anyway, so might as well just put it right down there, probably where the line between the B and the C come out. It'd be nicer if these coordinates were a little tighter, but they work fine, and we don't use them all that often. So I'm going to, well, while I'm here, I guess I could actually go grab another component. The component we want is going to be the SN74LS. I'm just going from memory here. LS08N. And I guess maybe I don't need this SN. I believe that means signetics. It's a Signetics product. We don't care whose product it is, but it's going to be a 74LS08N. Now that N, if I remember right, and I probably don't, means what it's made out of. And I think that's plastic, but it could be made out of plastic or ceramic or metal. And I let students know that the top selection there is if you want several of them in a chip. I don't. What I want is a single gate, so I'm going to click on the bottom one. There's my AND gate symbol in the window. Going to double click on that and then click A on this little box that shows up. I'm going to put my AND gate, I don't know, maybe line it up where well, I'll show you that in a minute. Let me cancel this. I don't need any more. Cancel this for now. Well, let's see. This line on the bottom of the AND gate, maybe we could line it up between the 2 and the 3 and somewhere between the power and the ground. So roughly around here. We're also going to need some switches. Debating on, well, I think I'll shift gears really quickly and talk about what these numbers mean. First of all, the number below here shows us that this is an 08. It's an AND gate, a multiplier. The number above is Multisim trying to actually give components numbers so that we can refer to them by a handle. But this is also a good opportunity for me to mention to students that if you double click on these components and then click on the label, display on the display tab, you can actually turn these numbers off. For example, I will click on the radio button for use component specific visibility settings, and then if I want to show, I could actually click here, unclick the show values, and click OK, and notice the name of the chip. It's an 08. It goes away. Maybe I don't want that to go away right now. I'm going to double click again and put that back. But the UA at the top apparently is called a reference designation. So I'm going to turn that off. Show ref des, turn it off. And I'm going to click OK. And so I don't need that for such a small circuit. Okay, so now let's put some switches on here. So I'm going to right click and click place component, and the switch I want is going to be a single pole double throw. And to get that, I'm going to put SPDT for single pole double throw. It has 3 options here, one that's normally closed, one that's normally opened, and just the regular SPDT. That's the one I want. That's the one in the window. Double clicking on that, and I'm going to have to, I think I'll put my switch right here. I accidentally double clicked on it. But I don't need that. So I'm going to close the selected component window. Now let's talk about a couple of things that we want to do to this. It's automatically going to be called switch 1. I think I'll leave that there. But one thing I really need to do is, I always get this wrong. I think I'll get it right this time. I want to flip that thing horizontally. How did I find that? I'm right clicking on it and I'm going to flip it horizontally. That just flips it around. It basically puts a handle on the horizon. You grip it by the horizon and you flip it the other direction. That's why it says flip it horizontally. This is switch 1, and it says key equals space. And what that means is if I hit the space bar, that actually controls the switch. What I like is I like this key space to actually be a little closer to the component. So I can click on that and I can move it. And I can, let's get a hold of it here. I can actually move it with the arrow keys too. And I think I'll move it a little closer. Okay, so I've got a switch. I want another one. So I'm going to select the whole thing, right click, copy, right click again, paste, and then I want this switch to be exactly below that switch. Automatically designates it as S2. If you want to keep these S1 and S2, sometimes I can just put that there to remind me that that is switch 1. I can put that there to remind me that's switch 2, and then I can actually move them a little closer to each other for efficiency and elegance sake. Now, I'm going to hook this thing up. And it's pretty easy to hook this thing up. Hard to explain, but easy to demonstrate. To hook it up, I need wires. And wires have different names. Maybe you should write this down in your books. Write these notes down. Wires are called net. They're also called conductor. So I'm going to click on the top input throw and then release. And then I'm going to draw that net or that wire here. And I didn't have to click or anything. I just turned the corner at that point. And I'm going to click. And now I've got VCC from power going into the first throw of this switch. The bottom switch, I want to hook that up also to power. The top connection, I'm doing the same thing. Coming over here, turning the corner, and hooking up to the original elbow there because that's probably the closest place that I can access power. Need to ground these other two, so the bottom throw of the top switch, I click on that, come over here, come down here, click on that, and that connects that switch. And this one, I'm going to just click on it and also ground it. So the bottoms are grounded and the tops are powered. For elegance, what I like to have students do is select the components and just move them so that there is a minimum of what I call one click of space, so that one click of space shows beyond of wire shows. If we, I'll explain it again later, but I'm trying to reduce how much wire, and therefore it makes it a little easier to troubleshoot. So I'm going to click on this bottom one and do the same thing, drag it in, but you can see the ground gets in the way. So I'm going to move that ground around a little bit more later on, but I'm just using the arrow keys to move it down. Click on the space, not the ground, click on the space, click on this, come on, space, there we go. Click on the space and move the two switches parallel to each other vertically. So these little holes here are lined up with these little holes here, and that makes it look nice, elegant, and it is efficient. I also want to hook that up to this AND gate, which is really the intelligence that we're employing. And I'm going to click on that key, or on that, and hook that up to the top one, and put another input to the lower switch. Hitting the space bar will activate these, and up is going to be interpreted to be a 1 in binary, and down is going to be interpreted to be a 0 in binary. But we don't want the space key to control both of them, because there's no way to get other combinations of 0 and 1s other than both zeros or both 1s. So we need to change what controls these switches, what keys control these switches. And I think what I'll do is make these switches be controlled by this top one, maybe just the number 1 on the top of the keyboard, and then the one down here controlled by the 2. To do that, I'm going to double click, and when I do, I can click on value, and the value tab, you can see key for toggle, it says space here. I can make that a 1, but I'd have to go clear to the bottom of the list to get a 1. So it's just a lot easier just to type a 1 right there. And then click OK. And now, well, that moved it around. That actually, I need to move that back. Put that back up here. So I selected it, I'm moving it up, and I'm putting it up here. So I know that the 1 key, let's center it on there. Key 1 is going to control that. And I guess maybe I need to move this back into place. Don't know why. It's kind of strange. And actually this, I'm a little obsessive about making a tight ship. So I'll move those things in. I got 1 click before the corner, 2 clicks, but the switches are as close as I can get them, so the vertical on that can't be reduced. Generally, I like to have 1 click that comes out, but I can see that this is connected, so we'll call that good. This other key, space, I want to change that one as well. So I'm going to double click on that and space. This time it'll be the 2 key. So I'll just hit the 2 and now it's controlled by 2s. No, it's not. Double click again. Oh, I put it in the wrong one. So, cancel. Control Z undoes. And double click again. There it goes. And over here, I'm just going to put in a 2. Okay. And I said okay. And there it is. And it messes everything up again. But I can move things back where I need them. And then this key 2 goes here. And I can fine tune it with the arrow keys. I'm curious about why it doesn't seem to line up with the one above, but we'll go with it. Okay. So, S2, don't like where that is. Let's move it down here. And try our keys. Controlling, hit the 2. There's controlling 1. So this is the number 00. And of course that ski-wampus AND gate because I messed things up here. Let me see what I can do here. I guess if I get too close, it doesn't like me to move stuff. Okay. So now, take this switch, if it'll let me, there we go. And push that back out, push that back up, and I don't like how that looks. So click on this. Trying to get a hold of that switch. There we go. I'm going to move it back down there. Okay. So we got key 1. Maybe I bring that down, take up space, make it not quite so tight. This key 2, maybe pull it up there and line those up. And we got switch. What do we got here? Okay, maybe move this out this way. Okay. So I've tightened it up. It looks good. I could actually make it more efficient by pushing the VCC down, I think. I can move this around if I want. See what I can do with that. Fine tune with the keys. So now I know VCC is 5 volts and everything is... I'm trying to make this as small as possible for a few reasons. And one is troubleshooting. I don't like that again. And there we go. Now the ground, I probably could also push it up, but there I know something's coming, and so I'm just going to leave it down there till later. Okay. We now have a logic gate, the AND gate, and the AND gate can multiply 0 times 0, which would be a 0, 1 times 0, which would be a 0, 0 times 1, or 1 times 1, which would be a 1, the only instance where it would be a 1. So we're just proving this little logic gate, this little AND gate. Now, we want to put an indicator out here, and of course an indicator that we'll want is going to be a LED. And I'm going to avoid the rated ones for now, unless there's a problem, then I might switch over. I tell students that any color is fine. Yellow I don't like, and infrared I don't like, and just a clear one I don't like. So I think I'll try a nice red one. And that shows in the window the one I want. And I will double click. And there's my light emitting diode. That's the schematic symbol for light emitting diode. And I'm putting that in now. And let's close this window for now. So this light emitting diode, I want it, the power, let me say it that way, the power flows through it the direction of this arrow, but a diode is a one-way switch, and that's what this horizontal line means, is it's not going to let the power flow through backwards. Now, later on I'll explain why I didn't want to call that the electron flow, because that is a conventional flow direction, not a true flow direction, but I'll explain that later. But what I do want to do is rotate it. And I double clicked, I should have right clicked. And I want to rotate this counterclockwise 90 degrees. And then Another way to hook up wire is to make them touch. Unfortunately, sometimes after you make them touch, they don't hook up, which is why I tell students, always after you hook up the wire, make sure there is one click. Let me talk about what I mean by a click. The length of this red wire right here is one click, and it's really, I don't see them here. I wonder if it would be too much to click view and then show the grid. So supposedly, well, I can see the grid, kind of hard to see. We can zoom in a little bit, maybe see it a little better, but it's just not showing its grid very well. But the distance between two dots on the screen is a click. And so I say always make one click show, because if you got two components touching and you're assuming that they're hooked up and they're not, then you got to dig around to find out what's wrong with this circuit. It's less troubleshooting if you just make sure there's a click of net or wire between them. Now, an LED uses about 2.5 volts, and our supply uses 5 volts. So that means we would have 5 volts coming out of this AND gate because it needs 5 volts to operate. And that's a little too much for the LED. So what we're going to do is reduce some of the voltage in the electrons that are flowing. And to do that, it really doesn't matter which side of the LED you put a resistor on. But I'm going to put it on this side, which seems counterintuitive, except that, well, I guess I probably shouldn't open that can of worms and the conventional direction versus the true flow of electrons. But I'm just going to put it here. So I'm going to right-click, and I'm going to find a resistor. Now, the resistors, you kind of have to go to basic group, and then you scroll down here until you find the resistor, and we're going to click on that. And we got lots and lots of numbered resistors, and it's showing us a 1K as a default, which I will use. So I'm going to double click on that. Here's my resistor. I'm going to put it right there. I don't need anything else. Now the 1K resistor might work or it might not, but I like students to change this in several ways just so that they learn how. So what I'm going to do is, as soon as we have a resistor, I'm going to double click on the resistor, and I'm going to change its resistance. It's 1K, which is the same thing as 1,000 ohms. I'm going to change it to a 322 ohm resistor, and make sure you don't say 322K or 1,000 ohm resistor. That's too much resistance. And then click OK, and so it's pretty easy to change that. Now Multisim wants to call this resistor 1. I don't think it's necessary, and I would like students to have some practice in turning that off, and that is the ref des, which is here. And I'm going to click that, and that turns that off. I'm going to keep it as a 322 ohm resistor because you need to know what is the resistance of resistors. And now I'm going to make it elegant by using the arrow keys to make sure there's only one click of net or wire between those components. Okay, so I put a lot of effort into making this an elegant circuit, and I'll talk about some rules of elegance in a moment. But this circuit is effectively finished. All I have to do is ground this output. So the power will come through the VCC, flow through all of this, and I just need a way back to ground. Now, to make this efficient, I'm going to click on the ground and push it up. So there's one click from the ground to the connection point. Need to talk about that. These wires that cross each other are not connected. These wires are connected, and it has to do with that little dot. And you might have seen schematics show a little bridge over them. That's not what Multisim does. They show the dot, and the dot means they're connected. And if there's no dot, they're not connected. Okay. Also, a question my students have with this is, well, if you put a resistor here that drops the voltage for the LED1 down to 2.5, aren't you also dropping the voltage back down to 2.5? And this component, this AND gate, needs 5 volts. So the answer to that is that hidden behind and not showing and implied and assumed is that this AND gate is also powered and grounded behind the scenes. But that's a lot of wires to put on here. And since it's powered and grounded, just like a toaster or a vacuum cleaner, you got to plug them in to make them work. And the ground there is the ground that the AND gate uses, and so that ground helps it to maintain its 5 volts. It's only beyond that where we need to reduce the ground, which is why we have this resistor to do that. Okay, so we have a circuit, and now we want this AND gate to multiply. That'd be nice if it did what it's supposed to do, and it's seems intuitive that if you just hit your keys, 0 times 0 is 0, and 0 times 1 is 1, and then 0 times 1 is 1, and 1 times 1 is 1. The only time you're going to get a 1 times 1 is 1 through here is if both the switches are on. The problem is, a 1 means that these two little arrows should light up to indicate that we're multiplying 1 times 1, and the answer should be 1. Any other condition, any other combination of these switches would make 0 times something, and that would make sure these switches are off. Why doesn't it work? Well, the explanation to that is to consider a photography snapshot camera to a video camera. I like to call this snapshot mode because even though we can actually change the switches, it isn't actually updating the results of the switches with a fresh new image. It's like taking a snapshot with a camera. The thing is that you can only edit in the still mode, and you can only see the switch work in the video-ish mode. How do you get into the video-ish mode? You click this little green button here at the top, and that switches the mode to run the application. Now I can multiply. So I'm going to turn both switches off by hitting the 1 and the 2 key, and that's 0 times 0, and the result should be 0, and it is. Then I've got 1 times 0, and anything times 0 is 0, so the output should be 0. And then I've got 0 times 1, and the output should also be 0, because anything times 0 is 0. Now, the moment of truth. The top key, I'm going to switch that to 1, and it should turn the lights on, and it does. So this little logic gate is doing its thinking. It is multiplying the zeros and the ones that it inputs and giving us the correct answer. So there we go. The first circuit. We've made one. And I'm going to turn this off because I'm going to do some editing. And what editing am I going to do? Well, that took a long time, and it shouldn't have to take that much time. What I want to do is I want to make a copy of this and then edit that copy and keep this original the same way. To make a copy of this original, generally I can just tell students copy it and paste it to the right of itself. I'm going to click and drag across the circuit, and that selects the entire thing. Then I can right-click and copy, and then out here I can right-click and paste, and then I can put it, I'm going to align it roughly the same height and beside the other circuit, maybe fill up the space, click, and there it is. What I want to do now, both these circuits will work. if we were to put it into the video mode, what would we call that? The presentation mode, the action mode, I don't know what we call it. I call it the video mode. In any case, what I want to do now is delete the LED and delete the resistor, which automatically deletes the ground wire. And even though on a real circuit, if we were to put this on a breadboard, we would actually have to use an LED on the breadboard, and we would actually have to use a resistor on the breadboard, and the output of the resistor would have to be led back through a net wire back to ground so it would work. But there's a shortcut that cleans this all up quite well, and that is something called a probe. Right click. I don't need this window. Right click, place component, and up in the component window I'm going to key in. You might want to write this down so you can refer to this note later, but okay, got probe, didn't find anything. The reason it didn't find anything is because the normal state of group should be all groups, and then that went back to LED, but I don't want LEDs, I want probes. So now I got probes. This probe is a clear probe. I can't see them very well when I'm rushing around the room, so I tell students you're not allowed to use a blue probe. A clear probe. You can use blue. I say let's stay away from digital probes right now, but we're probably going to see an instance here in a minute where we're going to need one. The digital probe, let's just choose blue. Blue's nice. I don't know, red. We could choose blue, red, green. I don't like yellow. For me, that's hard to see, but orange is not too bad. So orange, green, avoid digitals, blue, and red. And yellow, but don't use yellow. I'm just going to use a red. Okay, so I'm going to click OK. That does the same thing as just clicking on the blue line for the selected probe. I'm going to click that, put it on the screen right now. The selected component window comes back to say, would you like another? And I just cancel it or close it. And what I like to do here is, and you don't have to, let's turn off that X1 for probe X1. I don't know, do we want that? No, we don't want that. So I'm going to double click just for some experience and turn off the ref des. And that goes away. Probes, we're going to assume that they're 2.5 volts. Maybe I'll turn that off too. Double click, come up here, show values, OK. Now it looks like the wire might have to turn a corner. And yeah, we can go that direction if we want. But for experience, I'm going to have students rotate that 90 degrees, bring it down here, and hook it up with one click of wire between. So now we got this probe on here, and I'm going to go into video mode, and I'm going to use my keys, my 1 and 2 key, to say, look, they both work the same. The probe's easier to see. There's no resistor on there. Why isn't there a resistor on the probe? It's implied that the probe has a built-in resistor. How come it doesn't go back to ground? It's implied that the probe has a built-in ground. So that just cleans up the screen a little bit and makes it nicer. So now using the switches, turn everything off. 0, 1, 2, 3. There are all the combinations. And the probe turns on when the LED on the other circuit comes on. So this thing still works with probes. We need to be aware that we sometimes have to hook up LEDs with resistors back to ground, but other times we can make things look even nicer with a probe. Okay, so now we got our second circuit built. Let's make another one. This is the AND gate. But hopefully I've hammered that into my students' heads enough that they know, just by looking at the shape of that, it's an AND, an 08. It's a multiplier. But what I want to do now, I won't be able to do unless I turn off the power. I want to copy this circuit. I want to right click and copy it, and then I want to paste it below itself. So I right click, click on paste. I'm going to put it maybe right here. Okay, got another one. Now, isn't that nice? This is about the time the students realize I can make a lot of circuits and I don't have to build them all from scratch. The copy and paste that's pretty nice. It is. But I want to build another circuit. I don't want this to be an AND gate anymore. I want it to be an OR gate. At that point, students are rushing to delete it and go and find an OR gate, but don't do that. It's faster to just double click on it. And then the window that comes open, you click the replace key, and now it says 74LS08. Well, the number for an OR is a 32. And there it is. I got my OR gate. I can just double click on that and click on A, and it changes the AND gate to an OR gate. And suddenly we're ready to do math with it. And so we'll turn it on. So doing the math with it, I got this window that opens. I just close it. The OR gate, it adds. And so I'm going to use my 1 and 2 switch to shut it off. And then I'm going to use it to add. Well, 0 plus 0 is 0. It's working because it's off. 0 plus 1, got to get on the right keys. 0 plus 1, well, 0 plus 1 is 1. So that's working correct. Also, 1 plus 0 is also 1. So there's 1 plus 0, and it's also 1. Now, the next part's confusing unless you saw my previous video where we said we're really talking about true and false here, and anytime there's a true, there's true. So true plus true is also true, which kind of implies that 1 plus 1 is 1. That'll be a problem that we'll resolve later, but just remember when you're thinking about this OR gate, true in plus true in is also true. So the OR gate is working well. Took us a long time to make that first circuit. Then with the magic and power of copy and paste, we can make more. Let's turn this off so we can edit. And I'm going to select this whole circuit, right click, copy it, right click over here and paste, put it where I want it. Oh, maybe right about there. And now I've got a new circuit to work with. The circuit that I'm going to do, well, the circuit I'm going to make now, we've got the 08, the 32. It just makes sense to do an inverter or a NOT gate next. To do that, I'm going to double click on the gate and click replace. And remembering that the NOT gate is the 04, should be hammered into my students' heads by now. There's the 04. Double click on the blue line, click on the A, and it switches the gate out. So now we've got a NOT gate. Remember, the NOT gate is the little circle. We always seem to put a buffer with it to strengthen the signal so we don't have to continually check to see where the signal went weak. It just makes sense. I think that's the reason. If any viewers out there know different, talk to me. Teach me something. I'd love to learn. Okay, so now I want to make this efficient again. So I'm going to click on that and bring it up here. Make sure there's one click of net or wire between these. I'm going to click on the probe coming up, clicking out. And now I've got that, but wait a minute. There's only one input on a NOT gate. What do we do with this thing? Well, that's easy. Kill it. Maybe. There we go. So select it, delete it. It goes away. This NOT gate can be made more efficient now. Move the ground. Maybe we don't want to cover the key. Okay. We're ready to test the NOT gate. Going to turn it on. Now, it's on, but this NOT gate inverts. So if we put a 1 in, we're going to get a 0 out. Switching the key to the 0, we put a 0 in, we're going to get a 1 out. The NOT gate is inverting, flipping. It's nullifying the input. It's flipping the input, giving us the opposite as the output. It works. We're going to do some more. So I'm going to stop the animation. And I think what I want to do is copy this NOT gate, right click, copy, paste it below this gate, maybe down here. Do I want to do that? Nope, going to Control Z. Think I'll do this differently. What I want to do is this gate. I want to take a copy of this OR gate, this adding gate, copy it, put it below itself, paste. Put it down here below it. Oh, maybe right around there. And what I want to do now is I want to take the output of this adding OR gate and invert it. So I'm going to come up here and right click on the NOT gate, copy it. I'm going to come down here and paste it. And I think I'll just put it right there. That's a strange place for it. And I don't know what's going on there, so I guess I better move stuff around. So I've selected the probe, I'm pulling it out, and by just plopping it right there, it has connected it. So that's kind of a quick way to connect it. Now, a 32N plus an 04, and I hope, especially if you're my students, you're thinking, wait a minute, isn't that an O2 gate? Well, yes, it is, because an O2 is simply an OR gate where the output is inverted, right? So I already have this whole, no, I don't. I want to copy this whole thing, right-click, copy, right-click, paste, and put another copy of this here. Only this time, I want to put a NOR gate here. Double-click, and replace, and the NOR gate is the 0, 0. Double-click, click, and now I have a NOR gate, but I want the two circuits to do the same thing, one with an expanded NOT, and this one I don't want that NOT. Get up, click on the probe, make it elegant. These two circuits should do the exact same thing. So I'm going to turn the circuit on. I did turn it on, and let's test this. With both inputs on, well, it adds first, so 1 plus 1 is 1. The output should be 1. True plus true is true. The output should be true, but then the result is inverted, so it'll be false. So the light off is correct. Let's turn them both off. With both off, 0 plus 0 is 0, but that's inverted to the opposite of 0, which is a 1. Let's go, there's 0, let's go 0 plus 1. Well, anything that's true in this case should come out of the OR gate as true. But the other circuit didn't work, did it? Okay. I think I know why. We'll talk about that in just a second. Maybe I should do it now. In any case, these two should be doing the exact same thing. Let's count through them in binary. 0, 1, 2, 3. Right? 0, 1. Okay, since they don't agree, let's find which circuit is correct. Well, 1 plus 0 should be a 1, and that should be a 1 here. And then that should be flipped over to be a 0. So this circuit is correct, and this one is not. I think the reason, I better turn this off so I can edit, is this probe. Double-clicking the probe, and I'm going to replace that probe with a digital red, and then I'm going to turn the circuit back on. Oh, I just realized my mistake. That's not it, but that'll be the solution later. I'm going to now turn this off and Control Z, and I think I'm back to the other probe. My problem is I put a NAND gate here instead of an OR gate. So we want to put a NAND gate here. So I'm going to double click on it, click on replace. That's a 02, not a 00. So I'm going to put a 02 here, double click, click A. There it is. These two circuits should be exactly the same. Let's turn it on and test it. Okay, this is 1, 1. I'm going to switch to 0, 0. When they're both off, 0 plus 0 is a 0. And if you flip a 0, you get a 1. And that's exactly what the NAND is doing. And now here's a 0 plus 1. 0 plus 1. Anding those two together. Well, that's a 1. So right here it should be a 1. That's flipped over to be a 0. And the other circuit agrees. 2. This is a binary 2. 1, 0. Well, 1 plus 0 is 1. And it's inverted to be a 0. And the last one, 0. No, this is 1 plus 1. True plus true is a true, so it should be a 1 here, which is flipped over to be a false here. And the NOR gate is actually following along and doing the same thing. So here is a NOR gate with an expanded NOT and OR gate, and this is the NOR gate itself. What else do we want? Well, we did a NOR gate. What have we done so far? We've got AND with an LED. Everything else with a probe, AND or NOT. Here we have a OR with a NOT gate or a NOR. They're the same thing. Let's do, how much space have I got here? I got plenty of space down here. Okay, so let's just copy both of these and paste them down below themselves. Right click, copy. Oh, got to turn this off, or I can't do that. Right click, copy. Can't edit in animation mode. And then I'm going to right click and paste. And down here I've got two circuits. Looks like I copied an extra ground. Don't need that. Select, hit the delete key. But I might just want to move these up a little bit. So I selected them both, use the arrow keys, and move things up. Okay, so same thing, but with a AND gate. So I'm going to double click on this one, replace it. An AND gate is an 08. So putting the 08 there, clicking, and there's my 08 with my 04. Over here, I don't want, well, this is an expanded NAND gate, and this is a compressed NOR gate. Double click on it, replace, and we want to use the one we mistakenly used before. I could edit that out, but we learned from it. So that is a 0, 0. Click OK, click A, and now we have our NAND gate over here and our NAND gate over here with the expanded NOT gate. Going to turn the power on and test this thing and turn this off again so I can see. And well, let's run through the numbers. I'm going to turn both keys off. What do we got here? 0 times 0 is a 0, inverted to be a 1, and the NAND gate is working correctly. Let's go 0 plus 1, 0, I'm sorry, I said plus 0 times 1 is 0, so there should be a 0 after the AND gate, and it's flipped over, inverted to be a 1, and also true with the NAND gate. flipping it over so it's a 1 times 0, and of course that's going to be the same answer. 1 times 0 is a 0 flipped over to be a 1. And then 1 times 1, well, that's 1 times 1. 1 times 1 is 1, and that's flipped over to be a 0. And so we just proved that the expanded and or does the same thing as the expanded NAND and NOT gate does the same thing as the NAND gate. Well, so far, so fun. What we want next, let's go for an XNOR exclusive OR gate. That means I'm going to right click on, I'm going to select all of this, copy it. I better turn this off. Turn video mode off, animation mode off, and paste. Looks like I got both of them. Evidently I didn't copy, but that's okay. We'll take them. Select everything, maybe slide them up a little bit. Okay. Now, this, of course, will be my XNOR, and this will be my XOR. So I'm just going to modify them, and of course, they should do opposite things. So double click, replace, and an XOR is an 86, which my students should know by now. Click OK, click A, and there it is, the 86, the XNOR, or the XOR. Well, now I've got a NOT gate on it, don't want that. So just select it, hit the delete key. Now push the probe back within one click, and we've got our XOR. Going to double click on this one and change that to an XNOR, not an XOR, XNOR. That will be a 266, almost the gate of the beast, but not really. That's my little joke. Okay, A, and we got the XNOR over here. And these two, since they are inversions of each other, I mean, they're both XORs, but this one has a NOT gate on it, they should do the opposite. I'm going to flip both switches down and turn it on. Now, these should be opposite of each other, but they're not. Maybe you can remember the solution since I mistakenly gave it to you a minute ago, but let's go with it for now. Let's go. When these are opposites, we should get a 1. And when they're the same, we should get a 0. This being inverted, when these are the same, we should get a 1, which we're not getting. And when they're different, we should get a 0. We're not getting the right answer from that. But let's just step through this one and then we'll fix the other one. Okay, so 0, 0, those are the same. 0, now they're different. It's a 1. The two gates have opposite inputs. Now the two gates have opposite inputs. And now they have the same input. So the XOR, which I like to call the XOR gate, but it's the XOR exclusive OR, is working correctly, but this XNOR gate is not. So to fix that, I have to edit it. So I have to turn the circuit off, double click on that, and now I'm going to replace that probe with a digital version, and that seems to work. And I'm still deciding whether I should just use all digital in the first place. But I vaguely recall somewhere along the course that was trouble. And so I just switch it when needed. But I could be wrong. Maybe they should have all been digital probes in the first place. Somebody message me and tell me that should work and give me rhymes and reasons, and maybe I'll edit this video. In any case, this circuit, I believe, will work now. Going to turn the circuit back on. Go back into animation mode. And let's turn it off and turn it on one more time. Probes do not plot to the grapher for interactive simulation. Connect an oscilloscope or run a transient simulator to graph for data. Well, it works anyway, so those are our messages. Don't matter. So let's try it. I'm going to count in binary 0, 0, 0, 0, and they should always be the opposite since one's just the inversion of the other. So 0, 0, 0, 1, 1, 0, 1, 1. So they are working correctly. So now I've got all these. I'm going to turn off the animation. I'm going to click on my scroll and zoom out. And I wanted to drag the screen, but it messed it up. So Control Z takes care of that. And I'm going to press down on my scrolly wheel and drag the screen down. And I could actually reduce the size of this screen, but I don't think I will. For my students, you have either date, period, seat number, and name at the top, and you have all of these circuits built. Now it's time to turn it in for points. How do we do that? Well, one thing I want to do is print it. You could submit it as a PDF as well, but I like to have students in the classroom print this thing, and then I just go collect them out of the printer. But remember, with this 11 by 17 page, I know it's going to print out on a single page, but sometimes students aren't sure, so they want to click on Print Options, go on to Print Sheet Setup, and just make sure it's not going to print 4 pages. It'll print 1. It'll fit 2 page. Click OK. And then I'm going to click my Print button up here. And that's a quick way to print. I can hear my printer going. And so I've got this. This is where I would have my students turn this in, and I would give them points for making all of these circuits. Okay. So in my classes, this might be different in other parts of the world, but in my classes, students always save your work in at least 2 places. If you save things on the computers, well, the techs in the background, they like to clear that off once in a while, so it's a bit of a risk. I suggest students have a flash drive and always save their work in 2 separate places. The reason for that is we lose our flash drives. So the second place could be your Google Drive, or you could email it to yourself. Both of those options actually require you to save this onto the computer somewhere and then either attach it to an email that you send from yourself to yourself, or you can then drag it right into a Google Doc page or a Google Drive somewhere. But to do that, you have to save it on the desktop too. I'm going to click on File, and then I'm going to click on Save. And it says, where do you want to save it? And I'm going to click on Desktop. I got a bunch of stuff on there. And then I can just save it with its name, give it a name, first circuits or something, save it, and then it can be saved. It's saved. And then you can pull it from there, email it to yourself in a pinch, or drag it into your Google Drive. Okay, so that's it. But there's a couple of things I also want to talk about before I'm done, and those things are here. I want to review elegance, and whenever I have red words, that means students need to write those down. So make sure you record these in your logbook. For elegance, when we have elegance, we have something that is pleasant to look at, easy to troubleshoot, doesn't take up a lot of space on the page, doesn't look like an explosion of spaghetti factory. These are my rules of elegance. First, no less than 1 click of net between components and connection dots. So this is really just saying, show the wires, but make them as short as possible. to make them as close as possible, to make them as short as possible, you kind of have to move components closer to each other. That's the second rule. Move components as close as possible to each other without being on top of each other. Now, you can move the wires by clicking on them. But if you click on a wire, I guess I should probably show you that really quickly. Let's go back there and let's go click on a wire. I'm going to zoom into this one. And that's a good illustration. To move this wire, I just click on it. And then I can move the wire with my arrow keys. I used to could move the wire. I guess I can't. You have to drag it up and down. But I could move the wire down here if I wanted. Well, that's a bad thing because it's going over the top of the ground. But the point is, you can move the wire. Okay? Unfortunately, I don't want you to make diagonal wires. So if you grab the wire by the corner, you're making diagonal or slanted wires, and that's against my personal rules. So you're not allowed to do that. I'm going to put that wire back where it was by double Control Z a couple of times, and there it is. So that's what I mean by no diagonal net, only vertical or horizontal lines. Now, when you get better at this, when you get skilled, want to make your own circuits, I don't mind if you make your own circuits with diagonal lines. But for me, trying to troubleshoot things and keep this tight and clean and elegant, I want my lines to either be my net, my horizontal lines, my wires, my conductors. Make them horizontal or vertical only in this class. No looping net. That is, sometimes when you move a component, the wires like to tangle all around themselves, and that is a problem to be resolved. So you can do it, but fix it so that the wires are still straight paths whenever possible. And you need the easiest way, quite often when you move a gadget, twist it, rotate it, something, you get wires all over the place, just delete the wires and place them back. It's just simpler that way. 5, remove unnecessary annotations. We might want to keep voltages. We might want to keep the switch keys. You know, what keys flip the switches. But there's congestion with unneeded labels, so I encourage my students to turn them off if they're not needed. But if they are needed, they should be there. Number 6, retained labels can be moved to more elegant locations. You saw me move those labels around, probably more than you cared to see, but you can move them to better, more elegant locations. And the last one, 7, do not overlap components. Don't put a NOT gate over the top of an AND gate. Don't put wires, net, conductor. Don't make them run horizontally one above the other. Don't make them run vertically one above the other. You can cross wires. Remember, crossing wires, the dot means they're connected. No dot means they're not. And if you need to connect them, you actively connect one wire to another, and that automatically puts a dot over it, or just cross the wire and it won't put the dot over it. But those are my rules of elegance. Okay, so these are the circuits we just made, but I think we made more than this, so we don't need to do that. And so that's pretty much everything that I wanted to say in this presentation. And so I hope you learned a lot. For those who were not in class, this is how you do this at home. By the way, you can download Multisim at home. If you're my student, talk to me in class, and I will tell you how to download Multisim at home for your legal use. And for those of you who are not my students, you're going to have to go and figure out how to do it by negotiating with National Instruments. Okay, this is Aaron Jerome Electronics. You can reply to this video down below, or you can message me at jeromeelectronics@gmail.com. That would be JEROMELECTRONIX@gmail.com. Thanks for watching. See you in the next video.